Okay, we're now going to go into the customer panel, and we'd like to welcome Angelo Fausti, who's a software engineer at the Vera C. Rubin Observatory, and Caleb McLaughlin, who's senior spacecraft operations software engineer at Loft Orbital. Guys, thanks for joining us. You don't want to miss, folks, this interview. Caleb, let's start with you. You work for an extremely cool company. You're launching satellites into space. I mean, of course, doing that is highly complex and not a cheap endeavor. Tell us about Loft Orbital and what you guys do to attack that problem.
Yeah, absolutely. And thanks for having me here, by the way. So Loft Orbital is a company that's a Series B startup now, and our mission basically is to provide rapid access to space for all kinds of customers. Historically, if you want to fly something in space, do something in space, it's extremely expensive. You need to book a launch, build a bus, hire a team to operate it, have big software teams, and then eventually worry about, a lot of very specialized engineering. And what we're trying to do is change that from a super specialized problem that has an extremely high barrier of access to a infrastructure problem, so that it's almost as simple as deploying a VM in AWS or GCP is getting your programs, your mission deployed on orbit with access to different sensors, cameras, radios, stuff like that. So that's kind of our mission. And just to give a really brief example of the kind of customer that we can serve, there's a really cool company called Totem Labs who is working on building an IoT constellation for Internet of Things, basically being able to get telemetry from all over the world. They're the first company to demonstrate indoor IoT, which means you have this little modem inside a container that you track from anywhere in the world as it's going across the ocean. So it's really little, and they've been able to stay a small startup that's focused on their product, which is that super crazy, complicated, cool radio, while we handle the whole space segment for them, which just, before Loft was really impossible. So that's our mission, is providing space infrastructure as a service. We are kind of groundbreaking in this area, and we're serving, a huge variety of customers with all kinds of different missions, and obviously generating a ton of data in space that we've got to handle.
Yeah, so amazing, Caleb, what you guys do. I know you were lured to the skies very early in your career, but how did you kind of land in this business?
Yeah, so I guess just a little bit about me. For some people, they don't necessarily know what they want to do like earlier in their life. For me, I was 5 years old and I knew, I want to be in the space industry. So, I started in the Air Force, but have stayed in the space industry my whole career and been a part of, this is the 5th space startup that I've been a part of, actually. So, I've kind of started out in satellites, spent some time in working in the launch industry on rockets. Then now I'm here back in satellites, and honestly, this is the most exciting of the different space startups that I've been a part of. So always been passionate about space and basically writing software for operating in space, for basically extending how we write software into orbit. So
super interesting. Okay, Angelo, let's talk about the Rubin Observatory. Vera C. Rubin, famous woman scientist, galaxy guru. Now you guys, the observatory, you're way up high. You're going to get a good look at the southern sky. I know COVID slowed you guys down a bit, but no doubt you continued to code away on the software. I know you're getting close. You got to be super excited. Give us the update on the observatory and your role.
All right. So yeah, Rubin is a state-of-the-art observatory that is in construction on a remote mountain in Chile. And with Rubin, we'll conduct the large survey of space and time. We are going to observe the sky with an 8-meter optical telescope and take 1,000 pictures every night with a 3.2 gigapixel camera. And we are going to do that for 10 years, which is the duration of the survey. The goal is to produce an unprecedented data set, which is going to be about 0.5 exabytes of image data. And from these images, we'll detect and measure the properties of billions of astronomical objects. We are also building a science platform that's hosted on Google Cloud so that the scientists and the public can explore this data to make discoveries.
Yeah, amazing project. Now you earned a Doctor of Philosophy, so you probably spent some time thinking about what's out there, and then you went on to earn a PhD in astronomy and astrophysics. So this is something that you've been working on for the better part of your career, isn't it?
Yeah, that's right. About 15 years. I studied physics in college. Then I got a PhD in astronomy. And I worked for about 5 years in another project, the Dark Energy Survey, before joining Rubin in 2015.
Yeah, impressive. So it seems like your organizations are looking at space from two different angles. One thing you guys both have in common, of course, is software, and you both use InfluxDB as part of your data infrastructure. How did you discover InfluxDB, get into it? How do you use the platform? Maybe Caleb, you could start.
Yeah, absolutely. So the first company that I extensively used InfluxDB in was a launch startup called Astra. And we were in the process of designing our first generation rocket there and testing the engines, pumps, everything that goes into a rocket. And when I joined the company, our data story was not very mature. We were collecting a bunch of data in LabVIEW, and engineers were taking that over to MATLAB to process it. And at first, that's the way that a lot of engineers and scientists are used to working. And at first, that was like people weren't entirely sure that that was that needed to change. But it's something. The nice thing about InfluxDB is that it's so easy to deploy. So as our software engineering team was able to get it deployed and up and running very quickly, and then quickly also backport all of the data that we collected thus far into Influx. And what was amazing to see, and is kind of the super cool moment with Influx, is when we hooked that up to Grafana. Grafana is the visualization platform we use with Influx because it works really well with it. There was like this aha moment of our engineers who are used to this post-process kind of method for dealing with their data, where they could just almost instantly, easily discover data that they hadn't been able to see before, and take the manual processes that they would run after a test and just throw those all in Influx and have live data as tests were coming. And I saw them implementing like crazy rocket equation type stuff in Influx, and it just was totally game-changing for how we tested. And things that previously it would be like run a test, then wait an hour for the engineers to crunch the data, and then we run another test with some changed parameters or a changed startup sequence or something like that, became, by the time the test is over, the engineers know what the next step is because they have this just like instant game-changing access to data. So since that experience, basically everywhere I've gone, every company since then, I've been promoting InfluxDB and using it and spinning it up and quickly showing people how simple and easy it is.
Yeah, thank you. So Angelo, I was explaining in my open that you could add a column in a traditional RDBMS and do time series, but with the volume of data that you're talking about and the example that Caleb just gave you, you have to have a purpose-built time series database. Where did you first learn about InfluxDB?
Yeah, correct. So I work with the data management team, and my first project was to record metrics that measure the performance of our software, the software that we use to process the data. So I started implementing that in a relational database. But then I realized that, in fact, I was dealing with time series data, and I should really use a solution built for that. And then I started looking at time series databases, and I found InfluxDB. And that was back in 2018. Then I got involved in another project to record telemetry data from the telescope itself, which is very challenging because I have so many subsystems and sensors producing data. And with that data, the goal is look at the telescope hardware in real time so we can make decisions and make sure that everything's doing the right thing. And another use for InfluxDB that I'm also interested is the visits database. If you think about the observations, we are moving the telescope all the time and pointing to specific directions in the sky and taking pictures every 30 seconds. So that itself is a time series. And every point in that time series, we call a visit. So we want to record the metadata about those visits in InfluxDB. That time series is going to be 10 years long, with about 1,000 points every night, which is actually not too much data compared to other problems. It's really just a different time scale. So yeah, we have plans on continue using InfluxDB and finding new applications in the project.
Yeah, and the speed with which you can actually get high quality, images, Angelo. My understanding is you use InfluxDB, as you said, you're monitoring the telescope hardware and the software, and you say some of the scientific data as well. But the telescope at the Rubin Observatory is, like, pun intended, I guess, the star of the show. And I believe, I read that it's going to be the first of the next gen telescopes to come online. It's got this massive field of view, like 3 orders of magnitude times the Hubble's widest camera view, which is amazing. That's like 40 moons in an image. It's amazingly fast as well. What else can you tell us about the telescope?
Yeah, so it's really a challenging project from the point of view of engineering. This telescope, it has to move really fast. And it also has to carry the primary mirror, which is an 8-meter piece of glass. It's very heavy. And it has to carry a camera, which has about the size of a small car. And this whole structure weighs about 300 tons. For that to work, the telescope needs to be very compact and stiff. And one thing that's amazing about its design is that the telescope, this 300-ton structure, it sits on a tiny film of oil, which has the diameter of human hair. And that makes an almost zero friction interface. In fact, a few people can move this enormous structure with only their hands. As you said, another aspect that makes this telescope unique is the optical design. It's a wide field telescope. So each image has in diameter the size of about 7 full moons. And with that, we can map the entire sky in only 3 days. And of course, during operations, everything is controlled by software and it's automatic. There's a very complex piece of software called the scheduler, which is responsible for moving the telescope and the camera, which is recording 15 terabytes of data every night.
And Angela, all this data lands in InfluxDB, correct? And what are you doing with all that data?
Yeah, actually not. So we use InfluxDB to record engineering data and metadata about the observations, like telemetry, events, and commands from the telescope. That's a much smaller data set compared to the images. But it is still challenging because you have some high frequency data that the system needs to keep up. And we need to store this data and have it around for the lifetime of the project. So at the mountain, we keep the data for 30 days. So the observers, they use an InfluxDB instance running there to analyze the data. But we also replicate the data to another instance running at the US data facility, where we have more computational resources. And so more people can look at the data without interfering with the observations. I have to say that InfluxDB has been really instrumental for us And especially at this phase of the project where we are testing and integrating the different pieces of hardware. It's not just the database, right? It's the whole platform. So I like to give this example. When we are doing this kind of task, it is hard to know in advance which dashboards and visualizations you are going to need, right? So what you really need is a data exploration tool. And with tools like a chronograph, for example, having the ability to query and create dashboards on the fly was really a game changer for us. So astronomers, they typically are not software engineers, but they are the ones that know better than anyone what needs to be monitored. And so they use chronograph and they can create the dashboards and the visualizations that they need.
Got it. Thank you. Okay, Caleb, let's bring you back in. Can you tell us more about these, you get these dishwasher-sized satellites, you're kind of using a multi-tenant model. I think it's genius, but tell us about the satellites themselves.
Yeah, absolutely. So we have in space some satellites already that, as you said, are like dishwasher, mini fridge kind of size. And we're working on a bunch more that are, a variety of sizes from shoebox to, I guess, a few times larger than what we have today. And we do shoot to have effectively something like a multi-tenant model where we will buy a bus off the shelf. The bus is what you can kind of think of as the core piece of the satellite, almost like a motherboard or something, where it's providing the power. It has the solar panels, it has some radios attached to it. It handles the attitude control, basically steers the spacecraft in orbit. And then we build also in-house what we call our payload hub, which has any customer payloads attached and our own kind of edge processing sort of capabilities built into it. And so we integrate that, we launch it, and those things, because they're in low Earth orbit, they're orbiting the Earth every 90 minutes. That's 7 kilometers per second, which is several times faster than a speeding bullet. So we have one of the unique challenges of operating spacecraft in low Earth orbit is that generally you can't talk to them all the time. So we're managing these things through very brief windows of time where we get to talk to them through our ground sites, either in Antarctica or in the North Pole region. So we'll see them for 10 minutes and then we won't see them for the next 90 minutes as they zip around the Earth collecting data. So one of the challenges that exists for a company like ours is that's a lot of, you have to be able to make real-time decisions operationally in those short windows that can sometimes be critical to the health and safety of the spacecraft. It could be possible that we put ourselves into a low power state in the previous orbit, or something potentially dangerous to the satellite can occur. And so as an operator, you need to very quickly process that data coming in, and not just the live data, but also the massive amounts of data that were collected in what we call the back orbit, which is the time that we couldn't see the spacecraft.
We got it. So we'll talk more about how you use InfluxDB to make sense of this data from all this tech that you're launching into space.
So we basically, previously, we started off, when I joined the company, storing all of that, as Angelo did, in a regular relational database. And we found that it was so slow, and the size of our data would balloon over the course of a couple of days to the point where we weren't able to even store all of the data that we were getting. So we migrated to InfluxDB to store our time series telemetry from the spacecraft. So, that's things like power level, voltage, currents, counts, whatever metadata we need to monitor about the spacecraft, we now store that in InfluxDB. And that has, now we can actually easily store the entire volume of data for the mission life so far without having to worry about, the size bloating to an unmanageable amount. And we can also seamlessly query large chunks of data. Like if I need to see, for example, as an operator, I might want to see how my battery state of charge is evolving over the course of the year. I can have a plot in an Influx that loads that in a fraction of a second for a year's worth of data, because it does, I can intelligently group the data by a sliding time interval. So, it's been extremely powerful for us to access the data. And, as time has gone on, we've gradually migrated more and more of our operating data into Influx. So not only do we store the basic telemetry about the bus and our payload hub, but we're also storing data that for our customers, that our customers are generating on board about things like, one example of a customer that's doing something pretty cool. They have a computer on our satellite, which they can reprogram themselves to do some AI-enabled edge compute type capability in space. And so they're sending us some metrics about the status of their workloads, in addition to the basics like the temperature of their payload, their computer or whatever else. And we're delivering that data to them through Influx in a Grafana dashboard that they can plot, where they can see not only has this pipeline succeeded or failed, but also where was the spacecraft when this occurred? What was the voltage being supplied to their payload? Whatever they need to see, it's all right there for them because we're aggregating all that data in InfluxDB.
Yeah, that's awesome. You're measuring everything. Let's talk a little bit about, we throw this term around a lot of, data driven. A lot of companies say, oh yes, we're data driven, but you guys really are. I mean, you got data at the core. Caleb, what does that mean to you?
Yeah, so, I think the clearest example of when I saw this be like totally game changing is what I mentioned before at Astra, where our engineers' feedback loop went from, a lot of kind of slow researching, digging into the data to like an instantaneous almost, seeing the data, making decisions based on it immediately rather than having to wait for some processing. And that's something that I've also seen echoed in my current role. But to give another practical example, as I said, we have a huge amount of data that comes down every orbit, and we need to be able to ingest all of that data almost instantaneously and provide it to the operator in near real time. About a second worth of latency is all that's acceptable for us to react to see what is coming down from the spacecraft. And building that pipeline is challenging from a software engineering standpoint. Our primary language is Python, which isn't necessarily that fast. So what we've done is started, in the goal of being data driven, is publish metrics on how individual pieces of our data processing pipeline are performing into Influx as well. And we do that in production as well as in dev. So we have kind of a production monitoring flow. And what that has done is allow us to make intelligent decisions on our software development roadmap, where it makes the most sense for us to focus our development efforts in terms of improving our software efficiency, just because we have that visibility into where the real problems are. It's sometimes we've found ourselves, before we started doing this, kind of chasing rabbits that weren't necessarily the real root cause of issues that we were seeing. But now that we're being a bit more data driven there, we are being much more effective in where we're spending our resources and our time, which is especially critical to us as we scale from supporting a couple satellites to supporting many, many satellites at once.
Coach, so you reduce those dead ends. Maybe Angelo, you could talk about what sort of data driven means to you and your teams.
Yeah, I would say that having real-time visibility to the telemetry data and metrics is crucial for us. We need to make sure that the images that we collect with the telescope have good quality, and that they are within the specifications to meet our science goals. And so if they are not, we want to know that as soon as possible and then start fixing problems.
Yeah, so I mean, you think about these big science use cases, Angelo, they're extremely high precision, you have a lot of granularity, very tight tolerances. How does that play into your time series data strategy? Yeah,
so one of the subsystems that produce the high volume and high rates is the structure that supports the telescope primary mirror. So on that structure, we have hundreds of actuators that compensate the shape of the mirror for deformations. That's part of our active optic system. So that's really real time. And we have to record these high data rates, and we have requirements to handle data that are a few hundred hertz. So we can easily configure our database with milliseconds precision. That's for telemetry data. But for events, sometimes we have events that are very close to each other, and then we need to configure database with higher precision, for example, microseconds.
Yeah, so Caleb, what are your sort of event, intervals like?
So I would say that, as of today on the spacecraft, the level of timing that we deal with probably tops out at about 20 hertz, 20 measurements per second on things like our gyroscopes. But I think the core point here of the ability to have high precision data is extremely important for these kinds of scientific applications. And I'll give an example from when I worked on the rockets at Astra. There, our baseline data rate that we would ingest data during a test is 500 hertz, so 500 samples per second. And in some cases, we would actually need to ingest much higher rate data, even up to like 1.5 kilohertz. So extremely high precision data there, where timing really matters a lot. And one of the really powerful things about Influx is the fact that it can handle this. That's one of the reasons we chose it, because there's times when we're looking at the results of firing where you're zooming in. I talked earlier about how in my current job, we often zoom out to look at a year's worth of data. You're zooming in to where your screen is preoccupied by a tiny fraction of a second. And you need to see the same thing as Angelo just said, not just the actual telemetry, which is coming in at a high rate, but the events that are coming out of our controllers. So that can be something like, hey, I opened this valve at exactly this time. And that goes, we want to have that at, micro or even nanosecond precision, so that we know, okay, we saw a spike in chamber pressure at this exact moment. Was that before or after this valve opened? That kind of visibility is critical in these kind of scientific applications, and absolutely game changing to be able to see that in near real time, and with a really easy way for engineers to be able to visualize this data themselves without having to wait for us software engineers to go build it for them.
Can the scientists do self-serve, or do you have to design and build all the analytics and queries for your scientists?
I think that's absolutely, from my perspective, that's absolutely one of the best things about Influx, and what I've seen be game changing is that generally, I'd say anyone can learn to use Influx. And honestly, most of our users might not even know they're using Influx, because the interface that we expose to them is Grafana, which is a generic graphing, open source graphing library that is very similar to Influx's own chronograph.
Sure.
And what it does is it provides this it's a very intuitive UI for building your queries. So you choose a measurement and it shows a drop down of available measurements, and then you choose the particular fields you want to look at, and again, that's a drop down. So it's really easy for our users to discover, and there's kind of point and click options for doing math, aggregations. You can even do like curve fit kind of predictions, all within Grafana, the Grafana user interface, which is really just a wrapper around the APIs and functionality that Influx provides. So yes, absolutely, that's been the most powerful thing about it, is that it gets us out of the way, us software engineers who may not know quite as much as the scientists and the engineers that are closer to the interesting math. And they build these crazy dashboards that I'm just like, wow, I had no idea you could do that. I had no idea that, that is something that you would want to see. And absolutely, that's the most empowering piece.
Yeah, putting data in the hands of those, who have the context, the domain experts is key. Angelo, is it the same situation for you? Is it self-serve?
Yeah, correct. As I mentioned before, we have the astronomers making their own dashboards, because they know exactly what they need to visualize. And I have an example just from last week. We had an engineer at the observatory that was building a dashboard to monitor the cooling system of the entire building. He was familiar with InfluxQL, which was the primarily query language in version 1 of InfluxDB. And he had that was really challenging because he had all the data spread in multiple InfluxDB measurements. And he was like doing one query for each measurement and was not able to produce what he needed. But that's the perfect use case for Flux, which is the new data scripting language that InfluxData developed and introduced as the main language in version 2. And so with Flux, he was able to combine data from multiple measurements and summarize this data in a nice table. So yeah, having more flexible and powerful language also allows you to make better visualizations.
So Angelo, where would you be without time series database, that technology generally? Maybe you could specifically InfluxDB, it's one of the leading platforms, but would you be able to do this?
Yeah, it's hard to imagine doing what we are doing without InfluxDB. And I don't know, perhaps it'll be just a matter of time to rediscover InfluxDB.
Yeah. How about you, Caleb?
Yeah, I mean, it's all about using the right tool for the job. I think for us, when I joined the company, we weren't using InfluxDB, and we were dealing with serious issues of the database growing to an incredible size extremely quickly, and being unable to, even querying short periods of data was taking on the order of seconds, which is just not possible for operations. So, a time series database is, if you're dealing with large volumes of time series data, a time series database is the right tool for the job, and Influx is a great one for it. So yeah, it's absolutely required to use for this kind of data. There's not really any other option.
Guys, this has been really informative. It's pretty exciting to see how the edge is. Mountaintops, low Earth orbits. Space is the ultimate edge, isn't it? I wonder if you could answer two questions to wrap here. What comes next for you guys, and is there something that you're really excited about that you're working on? Caleb, maybe you could go first, and then Angelo, you can bring us home.
Yeah, absolutely. So basically what's next for Loft Orbital is more satellites, a greater push towards infrastructure, and really making, our mission is to make space simple for our customers and for everyone. And we're scaling the company like crazy now, making that happen. It's extremely exciting time to be in this company and to be in this industry as a whole, because there are so many interesting applications out there, so many cool ways of leveraging space that people are taking advantage of. And with companies like SpaceX and the now rapidly lowering cost of launch, it's just a really exciting place to be. And we're launching more satellites. We are scaling up for some constellations, and our ground system has to be improved to match. So there's a lot of improvements that we're working on to really scale up our control software to be best in class and make it capable of handling such a large workload. So yeah, what's next for us is just really 10xing what we're doing, and that is extremely exciting.
And anything else you're excited about? Maybe something personal, maybe another tidbit you want to share? Are you guys hiring?
We are absolutely hiring. So we have positions all over the company. So we need software engineers. We need people who do more aerospace specific stuff. So absolutely, I'd encourage anyone to check out the Loft Orbital website if this is at all interesting. Personal wise, I guess I don't have any interesting personal things that are data related, but my current hobby is sea kayaking. So I'm working on becoming a sea kayaking instructor. So if anyone likes to go sea kayaking out in the San Francisco Bay Area, hopefully I'll see you out there.
Love it. All right, Angelo, bring us home.
Yeah, so what's next for us is really getting this telescope working and collecting data. And when that's happened, it's going to be just a deluge of data coming out of this camera and handling all that data is going to be really challenging. Yeah, I wanna be here for that. I'm looking forward. Like for next year, we have like an important milestone, which is our commissioning camera, which is a simplified version of the full camera. It's going to be on Sky, and so yeah, most of the system has to be working by them.
Any cool hobbies that you're working on, or any side projects?
Yeah, actually, during the pandemic, I started gardening, and I live here in Tucson, Arizona, and it gets really challenging during the summer because of the lack of water, right? And so we have an automatic irrigation system at the farm, and I'm trying to develop a small system to monitor the irrigation and make sure that our plants have enough water to survive.
Nice. All right, guys, with that, we're going to end it. Thank you so much. Really fascinating. And thanks to InfluxDB for making this possible. Really groundbreaking stuff, enabling value creation at the edge, in the cloud, and of course beyond at the space. Really transformational work that you guys are doing. So congratulations, and really appreciate the broader community. I can't wait to see what comes next from this entire ecosystem. Now in a moment, I'll be back to wrap up. This is Dave Vellante, and you're watching theCUBE, the leader in high-tech enterprise coverage.